Welcome to my project design. So basically, the project one asks us for a simulation for the page table, and when the memory is exhausted, we should develop some page replacement algorithm to handle the virtualization of the memory. Basically, a perfect project design for the operating system's memory virtualization. So in that case, we design. So first of all, we need a page table and a cache, which is um, which should contains the virtual page number, also called the VPN here. Um, here in the here in the design doc, we can see there's class. Maybe it's not class, it's a struct in C. So I I designed this page table. Should have 2 to the 32. That's 10 megabytes overall size, and then it can be split into 20s table entries, and then the other 12 serves as the other 12 bits serves as offset. Also, and most important thing is we should know the virtual page number, as long as the dirty bit, the valid bit, and the present bit, which also has initialization method. So when we call the first page table and the second page table, we can do the initialization. Also, the second page table should serve as a cache, which is when the user asks for a memory, ask for some size of the memory, it should first get converted into a virtual page number, which is why we have that. And then after that, we save the start pointer to the page table, and to this page table. So when we have the start pointer and the virtual page address, we can use the offset to locate the physical address of that chunk of memory. Okay. So other than that, we also need some metrics and functions to simulate the page replacement situations. That's when the memory, when we do not have enough memory, we still want to we still want to allow users more requirements for the memory. We need to use virtualization part, as long as develop some page replacement strategies, so that we can always have the most recently used or the current users, which is more significant to the current users processes, live in the cache, since it's faster. So in that case, we have the existing cache function, which will do nothing but scan the page table to see if the current frame get loaded into the cache or not. This should be done in the hash table, I guess, but in a more trivial solution, I would just use a iterable vector or a list, just to try to find the table entry in a finite array. The other one should be cache status. This is how I display all the status of the cache table. So I want to see what are the virtual page numbers instead of the cache table. So I know which one is most recently acquired and which one is the a previous required memory. So that's why that's how I do the replacement. And in the future, when I evict some unnecessary and significant memory, that will serve as my accordance. Other than that, we should have the page events. So basically, when we evict or acquire a new chunk of memory, I want to log them, and it should be stored in a file. So we can see, for example, an address number, and then acquire address number, and then evict an address number, then maybe replace. So we know exactly what happened when the user interact with the operating system or the memory system. Okay, and then the read count and write count, basically they are logger for the read or write requirements to the page table. Also head count, which is useful to calculate the missing rate. However, this is a simulation of the memory system, so it's not performance-oriented project. So maybe if we give a rather small cache table, when the size is not very significant, it can be so any kind of strategy will work, and the missing rate should not get increased or decreased, depend on the user's input. So for the page replacement strategy, I pick the FIFO queue like strategy algorithm. So when we have this cache, we can put our users requirements inside of the cache table box, and then we keep doing that. When the index get higher, it means the address, the memory the user acquired is more fresh. So if we keep doing that, we just need to put down whatever the user asks for into those into those little boxes. And after that, if we are exhausted with the size, we will just loop back to the first one, because we know the left side is will be the will be the oldest memory in this queue. So we can rewrite this, and then we keep growing, and then wherever we have to the most right side of this array, which is the higher index, it will have the most fresh memory requirements. So I also have the pseudocode. When the current page is not found, we know, okay, we have a page miss, and then we should increase our current pointer. Don't forget to use it mod to the cache size, so we can always have an invalid index. If there's nothing inside of the new cache chunk, which means it's an initialization, it's a warm-up setup, so we don't need to do anything. Otherwise, if there's something inside of the cache, we then have to evict that memory, which means we need to store it on our disk and then put something back. So that will be the logic unit to handle that part. Otherwise, most important thing is we need to get the new address into this new location. There shouldn't be a +1, but as you can see, after we increase the current pointer, we always want to get our new address into this cache, since since there's no others, like optimal strategy or the LRU strategy get involved. We can keep using this monotonic queue to determine where should we put the most recent acquired memory. So that's after that we can rewrite the memory's start address to that specific index. Thank you.